Transistors have much the same function as radio valves, but they have the advantage of being very much smaller and they work with very low voltages. Transistors were invented in 1948, but their origin dates back to the early days of broadcasting when radio receivers looked something like this. This receiver is called a crystal set because it uses a crystal detector. It consists of a coiled, springy silver wire known as the cat's whisker and a crystalline substance such as the natural mineral galena. When the cat's whisker touches certain parts of the crystal, the apparatus allows an electric current to flow more freely in one direction than the other. In other words, it rectifies or detects alternating current. Just how the crystal detector operated was never clearly understood, and with the introduction of the thermionic valve, the crystal detector soon became obsolete. This is an early 5-valve receiver. Since the time that this set was built, valves have been greatly improved and reduced in size so that modern receivers can be made smaller and more efficient. Valves are now used in all manner of electronic equipment, from television receivers containing 20 or more valves to computers like this one at the National Physical Laboratory, which has 5,000 valves. The variety of applications of the valve seemed almost limitless until the development of radar, when certain problems arose which could not be solved by the use of ordinary valves. The radio waves, usually used in broadcasting, are radiated at a frequency of from 30 kilocycles to 30,000 kilocycles a second. In radar, the frequencies may be 1,000 times higher. At these frequencies, ordinary valves cease to function properly, and in an attempt to solve this problem, crystal detectors in a modified form were once more brought into use, and they worked successfully. This stimulated research into how the crystal operated. Ultimately, this not only resulted in improved crystal rectifiers, or crystal diodes as they are called, but led the way to the transistor. The materials used in crystal diodes and transistors are known as semiconductors. The metal germanium here is a typical semiconductor. To understand its peculiar properties, we must consider why some metals, like copper, conduct electricity well, while other materials do not. To do this, we must study the structure of the atoms of these materials. Every atom consists of a central core or nucleus around which revolve a number of smaller particles called electrons. These electrons travel in orbits of different radii. Each electron carries a negative charge of electricity and the nucleus a positive charge. Only the electrons in the outer orbit play a part in the conduction of electricity. In copper, which is a good conductor of electricity, the electrons of the outer orbits are only loosely bound to their atoms and can move about at random in the spaces between the atoms. When a battery is connected across the two ends of the copper, electrons flow from the negative pole of the battery through the copper and back to the positive pole. The flow is not straight through the copper, but electrons jump from atom to atom. This flow of electrons constitutes an electric current. Now let us consider an insulating material such as porcelain. Here the electrons are tightly bound to their atoms and they can only be made to move with the greatest difficulty. When we connect up a battery, as we did with the copper, the atoms are under strain, but no current flows as there are no free electrons to carry it. Now we come to semiconductors. Under normal conditions, the conductivity of these materials is quite low. To see how this comes about, let us have a look at the atomic structure of germanium. The atom of germanium is tetravalent, that is, it has 4 electrons in its outer orbit. Each atom becomes bonded to 4 other atoms, each of the 4 electrons, as it were, bonding with a corresponding electron in a neighboring atom. The bonds in this crystal lattice are very strong, and few electrons are free for the conduction of the current. To increase conductivity, the number of free electrons must be increased. One way of doing this is by the application of heat, which causes the crystal lattice to disintegrate. Here is a piece of germanium in series with a battery and lamp. The lamp doesn't light up. Now we heat up the germanium with a flame, and soon the lamp glows brightly. More electrons have been released from the germanium atoms so that more current can flow. When the germanium cools, the current flow falls again. Heating, however, is not a satisfactory method of increasing or controlling conduction, and the problem has been solved in another and more ingenious way by the introduction of other atoms into the germanium. Atoms of the metal antimony, for example. Here is the germanium crystal lattice again, and here is an atom of antimony which has 5 electrons in its outer orbit. When introduced into the germanium crystal, 4 of the electrons of this impurity atom bond with 4 adjacent germanium atoms. The 5th electron is then free to leave the atom. Introducing a number of impurity atoms releases sufficient electrons to carry a current when an electric field is applied. The impurity atoms, because they give up electrons, are called donor atoms. A semiconductor like this, in which current is carried by free electrons, is known as N-type. N for negative carrier. Here is a piece of N-type germanium. Notice that it conducts current equally well in either direction without the application of heat. There is another type of impurity which also increases the conduction of pure germanium, the metal indium. Here is the germanium lattice again. The atom of indium, as you see, has only 3 electrons in its outer orbit. When introduced into the germanium crystal, the 3 electrons form bonds with 3 adjacent germanium atoms, leaving a 4th bond incomplete. There will be a space left where we are short of an electron. This space behaves as though there were a localized positive charge ready to capture an electron, and for this reason the region is termed a positive hole. Here are some more impurity atoms giving more positive holes. What we have done, in other words, is to create a shortage of electrons in the germanium. When an electric field is applied, as there are no free electrons available for conduction to take place, some electrons will have to leave their atoms, and when this happens, they leave behind them new positive holes. Some of the electrons will be captured by other positive holes. This process may be continued throughout the germanium, and at the same time that electrons are moving towards the positive pole of the battery, positive holes are moving towards the negative pole. Thus, we can think of the current flow as due entirely to the movement of these positive holes. In fact, we can go further and look upon these holes as positive carriers of electricity, free to move about this material just as electrons move about the N-type material. A semiconductor like this is known as P-type. P for positive carrier. The impurity atoms, because they try to collect electrons, are known as acceptor atoms. Here is a piece of P-type germanium. It looks like ordinary germanium, and current will flow through it in either direction, as with the N-type germanium. Now let us look at a diagram of a piece of P-type and a piece of N-type germanium side by side. Without any battery being connected, the positive carriers in the P-type and negative carriers in the N-type will move about at random. If we stop the movement, we can see that in the P-type germanium on the left there will be an equal number of positive carriers and stationary acceptor atoms. Similarly, in the N-type germanium, there will be an equal number of negative carriers and stationary donor atoms. Both pieces of germanium are therefore electrically neutral. Now let us consider what happens when we join the two pieces together. Some of the positive carriers will drift into the N-type germanium. Similarly, some of the negative carriers will drift into the P-type. If we now count up the positive and negative charges, we see that in the P-type there are more negative charges than there are positive charges, so the material has become negatively charged. In the same way, the N-type material has become positively charged. We can represent this state of affairs by an imaginary battery connected like this with a negative pole to the P-type germanium. Because of the electric field existing between the two pieces of germanium, more positive carriers are prevented from entering the positively charged N-type germanium. Like charges repel, remember. And similarly, more negative charges are prevented from entering the negatively charged P-type germanium. Now watch what happens when we connect a real battery like this, with the positive pole connected to the P-type and the negative pole to the N-type. The N-type germanium has now become negative with respect to the P-type germanium, and carriers can once more flow. Positive carriers to the N-type and negative carriers to the P-type. Now watch what happens when we reverse the battery. That is, connect the real battery in the same direction as the imaginary battery. Positive carriers will again be repelled from the N-type germanium and negative carriers from the P-type, so that no current flows. If we apply an alternating voltage, current will only flow in one direction. In other words, we can rectify alternating current. Here is a piece of P-type and N-type germanium joined together. You can just see the junction. If now we connect the P-type to the positive pole of the battery and the N-type to the negative pole, the lamp lights. If we reverse the voltage, the lamp does not light. The current only flows in one direction. This is the principle of the germanium diode. Here is one in its small glass protective cover. This matchstick gives you some idea of its size. The diode cannot, of course, amplify. To make this possible, we must add a third component, and when we do this, we have what is called the transistor. This diagram shows a piece of N-type germanium sandwiched between two pieces of P-type germanium. The P-type on the left is known as the emitter, the N-type in the middle the base, and the P-type on the right the collector. As before, we can represent the charges on the three components by imaginary batteries. Now a real battery is connected between the base and collector with the negative pole to the collector terminal, the condition for no current flow. A second battery is connected between the base and emitter with the positive pole to the emitter so that current will flow. In this particular type of transistor, it is arranged that there are far fewer electrons in the N-type germanium than there are positive carriers in the P-type, so that for our explanation we need only consider the flow of positive carriers or holes. Positive holes from the emitter flow into the base, There they will be attracted across the base collector junction into the collector because the collector is negative. With this resistance, we can control the number of positive holes to the base. These in turn determine the current which can flow in the base collector circuit on the right. Not all the positive holes from the emitter flow into the collector. Some of these remain in the base long enough to combine with free electrons there and become neutralized. This gives rise to a small current of electrons flowing into the base to replace those used up in the neutralization process. By varying the flow of electrons into the base, we can in fact control the number of holes which reach the collector. It is this control of positive holes which makes it possible for a transistor to amplify. Let us now look at some actual PNP germanium transistors. They are sealed in glass covers like the diodes. This lead goes to the emitter, this one to the base, and this one to the collector. With the cover removed, you can see the construction. There is a central strip of N-type germanium, and on the left, fused into it, is a small blob forming the emitter, and on the right, a larger blob forming the collector. And here is a transistor connected as we saw in the diagram earlier. That's the emitter, the base, and the collector. The emitter is connected through this milliammeter and a resistance, not shown, to the positive pole of a battery. The base is connected through this milliammeter to the negative pole of the battery. The collector is connected through this milliammeter to the negative pole of another battery, and the positive of the battery goes to the base. The emitter current, 4 milliamps in this case, splits up into two parts. The collector current of about 3.8 milliamps and the base current of about 0.2 milliamps. Now watch what happens when we vary the base current. Notice that a small change in the base current produces a large change in the collector current. This is the way we obtain amplification. The transistor can be used instead of an ordinary valve in all kinds of electronic circuits with many advantages. For example, any apparatus employing transistors can be made lighter and more compact. Not only because the transistors themselves are smaller, but because they require such a small power supply. This portable valve radio needs this low-tension battery and this high-tension battery to operate it. In the transistor radio here, this small low-voltage battery is all that is required to operate the receiver for an equivalent time. Another advantage is illustrated in large equipment like this electronic computer. When using valves, 5,000 of them in this case, quite elaborate ventilation systems are required to remove the heat generated by the valves. In transistor-operated equipment, there is practically no heat generated, and the transistors may be mounted close together on panels like this alongside the other components. One of the earliest applications of transistors was in hearing aid apparatus. This hair grip contains one, complete with amplifier, battery, and microphone. Transistors have developed rapidly, from small ones like this to the larger power-type transistors. Research into new techniques continues, and fresh applications are being discovered all the time.